Okay.
So, Professor Pavesi, is it okay now?
Yeah, now it's clear. Yeah, so I
Okay.
raised the volume. Yeah, with the age.
Right.
Yeah. Okay. How are you? How are you? Are you fine?
Oh, yes, I'm good. Yeah, we are good. The institute is also running very nicely, and most of the students, particularly research students, are back in the campus.
Oh,
So,
good. Good
so
sign.
yeah, good sign. At least most of the experimentalists are here. Some of the theory still are doing from home, and we are every week we are calling some students by phase.
Mm-hmm.
And of course, there are always some positive cases for the staff members, fortunately not the students till now. So things are, it's a dynamic situation, you have to cope with it.
Yeah.
Okay,
So
so
I think
yeah, right, yeah. We'll wait for a few more minutes, just before we start, okay?
yes.
Yeah, most of our faculty members and students are joining online, many of them through this link, and many of them will also join through probably YouTube. So, so good evening everybody. So before we formally introduce the speaker of the host colloquium, I have the pleasure of introducing our new chairman of the governing body, Professor B. N. Jagata. So as you know that this is an autonomous institute and we have a governing body, the chairs and the members. Yeah.
Yeah, thank you very much. Thank you very much.
We really wanted to meet physically as soon as possible,
Yes, surely.
but it's a very nice thing. The chairman was also from Department of Atomic Energy, and Professor
Hmm.
Jagdap was with the Department of Atomic Energy, DRC, as outstanding and distinguished professor as scientist, and right now he's the emeritus professor at IIT Bombay. So we are very happy to see you here in the both colloquium. This is our regular program.
My pleasure. My
Yeah.
pleasure. I'm too happy.
Yes. And you will see that from an annual report in future or future interactions that this outreach program and academic exchanges are actually one of our main tasks,
Good.
something ICTP Italy or something like that. So regularly we have this colloquium and memorial lecture seminars, but unfortunately things have slowed down this year. So we thought we must start. So we are very happy that you have joined our host colloquium today.
Yeah. Thank you
Okay.
very much.
So now it's my pleasure to introduce today's speaker, Professor Lorenzo Pavesi, and he is one of my friends and one of the collaborators for the last at least for almost 8 to 10 years probably. So for the other audience, Professor Lorenzo Pavesi is a professor of experimental physics at the Department of Physics, University of Trento, Italy. He received his PhD from Switzerland in 1990 and currently a full professor in the University of Trento. His main research interests in the area of silicon-based photonics, where he looks for the convergence between photonics and electronics. Recently, he is also interested in integrated quantum photonics and neuromorphic photonics. Professor Pavesi is author of co-authors of more than 500 publications with huge citations of more than 20,000 and impact factor for each index more than 73. He has written several books, at least 15 books, and several review papers. He is a specialty editor of the section of optics and photonics of Frontiers in Materials and in the editor advisory board of APL Materials. He is a fellow of the IEEE and is PIE of the SIF. It's good to announce that Professor Pavesi has a very strong collaboration with Indian researchers. I personally had 2 collaborative projects to Trento Advanced Research in Photonics. Currently, he has a project on quantum photonics with RRI and Bose Institute. So we are very happy that you have kindly agreed to talk on today's Bose colloquium. With this, Professor Pavesi can start.
Okay, thank you very much for this introduction. So I'm really happy to be here and to try to provide you my view on quantum silicon photonics. I'm particularly proud to give this talk within the frame of the Bose colloquium, since Bose was one of the father of modern physics. And actually, so the my idea is to go through the quantum silicon photonics, but before entering in the field of the lecture of today, so I would like first to introduce you to where I'm coming from. So actually, I'm coming from Trento, Italy. So Trento is a small town in the north of the Italy, and here you see the Alps. And so we are here in between the mountain. And I'm working at the University of Trento, which is one of the Italian universities. And according to different standards, so this university is has a quite good reputation, Italian-wise. So here I'm showing you the web page of my university and and the reason why is because here on the web page today you can look at and you see the fact that we have got recently a new research grant. So I'm happy that the university recognized the quality of the research that we are doing. So the university is Italian-wise is a small university. So we have essentially 11 departments that looks like a school. We have essentially 600 professors and 70,000 students. So if you are interested to know more about the university, so here are the links, the web page where you get more information about the university. But let's go back to the topic of my talk today. So today I would like to introduce you to quantum silicon photonics. And so the first argument is about photonics. And when I'm speaking about photonics, typically I'm not speaking about a label, a table full of optical components, but what I'm trying to do is that to squeeze all these components into a very small chip. So when typically I'm talking about photonics, what I'm talking about is integrated photonics. And the reason why I'm interested in integrated photonics is the fact that by using integration, so it is possible to produce devices that are small, that are cheap, and that can be easily integrated with nowadays technologies. But from a point of view of a physicist, as I am, the fact that we could use integrated circuit means that the optical setup is extremely stable, so you have a lower noise than in standard optics, and more importantly, so the losses are reduced. And all these fact makes that the device that you are producing are much more efficient than their macroscopic counterpart. So then in the title, I was stressing the fact that I want to implement these photonics by using silicon. And the reason why we are interested in silicon photonics is because silicon photonics can be fabricated. So the circuit can be fabricated by using the standard silicon processing. So this makes the process of fabrication stable, efficient, and less expensive than other semiconductor platform. At the very same time, so you can also leverage on the already deployed silicon semiconductor industry. That makes the fact that the chips that you are going to produce can be produced in large volume with low costs and still not compromising the performance of the devices. And finally, what is even more interesting is the fact that you can naturally merge on the same chip both the photonic as well as the electronics circuitry. And this is a quite important aspect. And indeed, in silicon photonics, we are following the same paradigm to success that has been followed by microelectronics in the last years. So here you see that microelectronics standard from separate components, that integrated circuit, and then massive integration and parallelism in the chip. And the same is happening nowadays in integrated photonics on the silicon platform, where in the last year of the last centuries, we have demonstrated different photonics devices. Then they have been integrated into chip, and nowadays we are with heavy integration of electronics and photonics on the very same circuitry. And here, just to show you an example of our research, so within a European project that is called IRIS, so we were able to integrate it in a single chip, a fully optical network that comprises more than 1,000 different photonic components that require more than 2,000 electronic blocks to reconfigure the optical network on the chip. This network was able to handle 48 different optical channels, and still everything was integrated in a very small area, so only few 10 of square millimeters. So this was the concept. Here is the wafer, so everything was manufactured on a wafer 8-inch in diameter, and then the wafer was merged with the electronic integrated circuit, and the two chips, so the photonic as well as the electronic chip, were bonded together. Then those two chips were packaged, were wired. So we, in this image, you see the chip, you see the optical fibers that are connected to the chip, you see the electrical lines, the electrical wires that brings in the electrical signal to the chip, and everything at the end is placed within a board where you can actually operate your optical network. And what you are seeing here is a fully functional optical network that is based on the silicon photonics. So this is what I'm meaning by silicon photonics. And in silicon photonics, but not only in silicon photonics, in microelectronics, so what are the next challenge that we are facing? So the scaling of dictated by the Moore's law has introduced a new challenge, essentially based on the fact that along the year, so the scaling of CMOS is hitting physical limitation. And what you are seeing here is a roadmap that has been proposed by IBM, where they are predicting the evolution of the microelectronic circuit as a function of the year, in such a way that during this evolution, the system performance is in each step improved. And what you see here is that by reducing, so scaling the dimension of the transistor in integrated circuit, so we are soon reaching the limit of 1 nanometer transistors. And then scaling down is no longer possible. And so what IBM is suggesting is that after reaching this wall, so the architecture of the computer and the basic principle of computing should be changed. And what you see here are two words that are two keywords in that are motivating my present research. And on one side, IBM is suggesting to go to neuromorphic computing, and on the other side is suggesting to go to quantum computing. So the future in integrated photonics is to try to face this challenge. So to go to neuromorphic computing on one side and to quantum computing on the other side. So neuromorphic means new computing scheme based on the way the brain is working. So those are essentially based on electromagnetic theory, so on classical physics. But what one is trying to do is to implement artificial intelligence into the photonic circuitry. And if you are interested on those topics, so please have a look to the webpage of our project where you can get the state of our research in this topic. On the other side, we have quantum computing. So this is a completely new scheme of computation that is based on quantum physics. And actually, a week ago, the Economist published a paper on a news on quantum computing, claiming that the quantum computing race is now open. And here you see many different approaches that are followed. So superconducting junction, you have cold gases, as well as photons. And so here is where the topic of today is essentially centered in. So let me start now with quantum silicon photonics and try to underline what are the main ingredients in this second quantum revolution that people is considering we are facing. So the idea here is to develop new technologies that are based on the fundamental properties of quantum system. And if I can be very, very simple, so those fundamental properties are essentially the fact that this technology should deal with single particle, meaning that we want to exploit the granularity of nature, we want to exploit the quantization of the energy. And so we want to use single photons in our devices. And then we want to exploit the fundamental properties of quantum mechanics, so the wave properties of the wave function. And in this way, so we want to use the state superposition, meaning that in computation, we no longer use the bit where you only have two states available, so 1 or 0 in the binary coding. So you have 1 or 0, and all the others values are errors. But instead, we want to use in quantum computation the state superposition, where your qubit can take any value between the state 1 and the state B. So state 1 and state 0. And here, so you have that your qubit is nothing else than a superposition of 0 and then 1. And so all the different superposition are available for computation. And actually another very important concept in this superposition is the fact that then at the end of your calculation, so you do collapse your wave function on a very well-defined state, and this collapsion is done by measurements. And then another properties that is a quite strange consequence of quantum mechanics is the strong quantum correlation between states of many particles. And this quantum correlation is called the entanglement. And so all these single particle entanglement state superposition are resources for enabling new devices. So then let me go to show you some examples, since I'm a physicist and I do want to go through, and I am an experimentalist, so I want to go to real actual experiments and actual evidence of the relevance of this second quantum revolution. So the first example is based on single particles, so on single photons. And the idea here is that to try to use quantum to enable to increase the security and communication. So one very critical aspect in the security of communication is the fact that nowadays what you do is that you use a key, and then you use this key to encrypt your message, and you send your message in such a way to the receiver, in such a way that an attack cannot read the content of your message. And the reason is because he has not the key that you have used to encrypt your message. And in order to generate this key, random numbers are extremely relevant. So essentially, you use random numbers to generate the key, and so that to enable cryptography. And in quantum, so the quantum key distribution is a very important issue because you have to be able to distribute this quantum key. But before going to the distribution, you need to generate the random numbers. And why quantum is important? Quantum physics is important because it is an intrinsically probabilistic theory. And so you can read in a textbook that the outputs of a quantum measurements are random. Meaning that, for example, a very simple experiment, you have a photon, you have a beam splitter, and then you cannot predict, unless in a probabilistic way, whether the photon is going through the beam splitter or the photon is reflected by the beam splitter. And so now if you record where the photon arrives, so you have the possibility to generate a random number. For example, if the photon is transmitted by the beam splitter, so this detector clicks, and so you have a 1. If the photon is reflected by the beam splitter, this detector clicks, and so you have a 0. And so the sequence of detection provides you the random number. Is this quantum experiment different from a simple tossing of a coin? And the answer is yes. Because if you want to build up a random number generator by looking at the result of tossing a coin, so your model is essentially a statistical model of what is happening. And actually, if you know all the starting condition, classical physics imply that knowing all the starting condition, classical physics tells you that you can predict the outcome of the toss. While the quantum mechanics is intrinsic probabilistic, so even though you know everything in your experiment, you cannot predict whether the photon is going here or there. And so you have that the quantum randomness is intrinsically in the quantum measurements. And so we want to use this concept in order to produce a quantum random number generator that is cheap, compact, and compatible. And so the idea is to use the spontaneous emission as a source of randomness. So essentially the idea is to look at the time when the photons are generated, the time when the photons are emitted. And this time cannot be predicted with certainty. And so by looking at that, so we can have our random number generator. And so the experiment was essentially based on the fact that the spontaneous emission is a Poisson process. And so provide that in a time interval, a photon is detected, then the time at which this detection event occurs is uniformly distributed. And so what we do is that we measure the conditional probability to have a detection event provided that one photon was detected. And so when the photon was detected, actually, is the source of our randomness. And so if the photon was detected in the first period, in the first time slot, so we have 1, in the second 2, and so on and so forth. So we do implement this technique by using an LED, a detector, and then some electronics to assign the different detection intervals. And then those sequence of detection intervals was our random number sequence. And so then we look at the randomness, and we did the analysis of the robustness of the random number generation process. So the first thing is that, so we produce our binary bits, our sequence, and then we pass the statistical test, and this provide us evidence that actually the random number that we are generating are really random. And then the second experiment was to change the condition of the LED in such a way to, for example, change the temperature, operating temperature of the LED. So the counts, so the photon emission is changed, and still the method, the condition, which is based on the conditional probability, was robust with respect to temperature variation. And so we have a random number generator that is random as well as robust with respect to external influence. And so then we move from the proof of concept, where we have a commercial single photon avalanche detector and a silicon nanocrystal based LED. We pass to the two chips that are one face to the other, two chips that are glued together, and then finally we have integrated everything into a single chip, where we have the emitters as well as the single photon detector that are integrated in a single electronic circuit. Everything is done in silicon, so this is the board that is used to test the quantum random number generator, and you see that everything is squeezed in a very small size. And still, is this useful? Yes. So here is an example of a device that is using quantum random number generator produced by a company that is called ID Quantique, and integrated within a mobile phone. So this is the Samsung Galaxy A Quantum that you can buy, and which use indeed QRNG, so quantum random number generator, to actually provide a secure link for a financial transaction. So here is an example of one of the devices that has been commercialized based on QRNG, therefore based on quantum physics. So another example is about entanglement. So entanglement, you know, is a characteristic of quantum physics where you correlate the degree of freedom of two different particles. And this quantum correlation is non-local, meaning that the two particles are can be in different locations. So they are actually two different particles. So what we are trying to do is that to demonstrate that there is another kind of entanglement that is between the two degrees of freedom of a single particle. And we want to show that this entanglement, so which is called single particle entanglement, is actually a resource for quantum information. So what is the physics here? So here the physics is essentially that you take one particle, in our case one photon, and then you exploit two internal degrees of this photon, which do not commute, in such a way to entangle those 2 degrees of freedom. So here the 2 degrees of freedom that are used in our experiment are the path, so the momentum, so where the photon is actually moving through, and the polarization state of this photon. And so we have to develop an experiment in order to, on one side, to produce this entangled single particle and single photon entangled state. Here you see how we proceed. So we generate a one photon, then we fix the polarization state of this photon, as well as the momentum, so the direction. And so in this way, we have our initial state. Then, by a beam splitter, we produce an overlap of these single photon states between the two momentum degree of freedom. So here we have the overlap, so the superposition of a photon that is moving in this direction, as well as the same photon that is moving in that direction. And then by using a polarization rotator, so we change the polarization state of the photon that is along this direction. And remember that we have only one single photon. So I should say that we change the polarization state of the degree of freedom of the photons along this direction. And so in this way now, we have between this point here and that point 2 and this point here, an entangled state, which is formed by a photon that is in this place here and has a zero momentum and an horizontal polarization with the same photon that is in this path here that has a vertical polarization and a one momentum. And so this is an entangled state between the 2 degrees of freedom of our photon and is a single particle entangled state. And then by using a Mach-Zehnder interferometer or an half plate, so we can project the state of our entangled photon in a very defined state of the momentum as well as of the polarization. In order to demonstrate that indeed we have a single particle entanglement, so we build up a setup in order to perform a Bell inequality measurements. And so in this way, so we can use the Bell inequality measurement to witness the existence of this single particle entanglement. So the experiment is simple. You have the generation stage here. So you have your entangled photon state here. And then you project this entangled photon state into a very well-defined momentum as well as polarization state. And then you analyze the state that you have produced. And in order to detect, so you measure whether you have that the outcome of your measurement is a photon in 1h, so in momentum 1 and horizontal polarization, or 1v, 0v, or 0h. And so in this way, so you can look at whether the state that you have produced here is indeed a single particle entanglement by doing a Bell inequality measurements. So here is essentially the outcome. So I do avoid the mathematics. So this is the correlation parameter between the different photon states. Here is the S parameter that you build up by projecting your single particle entangled state along the different Bell bases. And then this is the result that you have to look at. So whether your S parameter by doing the measurements is larger than 2. So if your S parameter is larger than 2, so then you violate the Bell inequality, meaning that you indeed have quantum entanglement between the 2 degrees of freedoms of your photon. And this is the result. And I want to underline that here, what we are doing is that we are performing this experiment by using an attenuated laser. And for a given condition of your measurements state, you see that you get an S parameter that is larger than 2. So here you violate the Bell inequality, here you violate the Bell inequality, here you violate the Bell inequality, here you violate the Bell inequality. So that means that the single particle entangled state produced by a laser beam so is indeed a quantum entanglement. But what is even here more interesting is the fact that we do obtain the same result if we change the light source. So we move from a laser to a simple halogen lamp, and still we are able to produce quantum single particle entangled states. Or even more interesting, so we can do and obtain the same result by using LEDs. So by using very simple light sources, so we are able to demonstrate that indeed, so we can make some quantum optics experiment and we can entangle single particle in this experiment. And what is here demonstrated is the fact that what you actually need in order to get this single particle entanglement is you need to preserve the coherence between the two different degrees of freedom. And indeed, in this example here, I do show the result when the light coming from the LED is not filtered by a very narrow spectral filter. And the reason why we want to use a very narrow spectral filter is that by using this filter, so we are able to increase the coherence length of the light produced by our LED. And indeed, if you do not preserve the coherence between the momentum degree of freedom, so you are no longer able to violate the Bell inequality. Is this useful for anything? Yes. So here is a scheme where we use our single particle entanglement in order to produce a random number. And so this is a quantum certified by the Bell violation quantum random number generator. And the idea is very simple. So we are tracing as a function of time the specific detector that is clicking. So we are generated our photons, our entangled photon, then we project the entangled state in a very well-defined state, and then we do look at where the photon actually is going. And if this detector is clicking, so we mark that this detector has clicked. If this detector is clicking, so we mark that this detector has clicked, and so on and so forth. And so by looking at which detector actually has detected the single photons, so then we are able to generate a sequence of random numbers. And since we are violating the Bell inequality, so we are able also to demonstrate that actually the entropy source in this experiment is of quantum nature. Then the second step is moving from the tabletop experiment that we are using to demonstrate the single particle entanglement into a small integrated photonic chip. So here we have 1 square meter, and then in the photonic chip, so we can reduce the size of the setup by several order of magnitude. From the experimental point of view, here you have a fully experimental table that you have to use to do the setup, while everything can be squeezed in a very tiny integrated photonic chip, which can be easily coupled to optical fiber to provide a simple experiment for the use of single particle entanglement. And this device here will be the source of a QKD experiment that we are performing within this Trento project for advanced research, where we have a fruitful collaboration with Professor Urbasi Signo in Bangalore and with several professors here, there where you are in Calcutta. So Professor Home, Professor Panigrai, and Professor Carr. So this is the experiment that we are planning to do in the near future, as soon as the integrated photonic source of single particle entanglement is tested. So I would like now to continue in this overview of our activity by showing another possibility to use the entanglement. And actually, what I want to discuss with you is to use entanglement in order to make on-chip single photon sources. So here the idea in our experiment is to make this a single photon source in the mid-infrared. And the reason is because we want to use this source for doing quantum sensing experiment in the mid-infrared. And the mid-infrared, the motivation why we want to go to the mid-infrared is because in the mid-infrared you have the typical absorption fingerprints of different molecular species. So carbon dioxide or oxygen sulfide, oxygen nitride, and so on and so forth. And the idea is to make this chip, this single photon source in the mid-infrared, but integrated on a chip, so that to make an on-chip quantum gas sensor. And why do we want to use entanglement to produce a single photon source? And here the reason is very simple, is because we want to produce what is called an heralded single photon source. So let us assume to have two photons that are correlated in time. So they are being produced at the very same time. And now, if we measure one of the two photons in the pair, now we are sure to have the other photon that is traveling inside our circuit. So here the idea is that to measure one of the photons in the correlated pair, so that to herald the presence of the other photon in your quantum circuit. And this is the reason why the source is called an heralded single photon source. So the measurements of one of the photons in the pair herald the presence of the other. And what is even more important is the fact that when we do herald the presence of the other photon, we remove from the statistic of the measurements of this photon all the vacuum states. So the statistic now of the measurements of this photon gets the typical one high peak at the single photon state shape of a single photon source. So in this way, so we can produce a single photon source by using a correlated in time photon pair. So this is the idea. Now we have to produce these on-chip correlated photon pairs. And to do that, we use a very well-known nonlinear optical phenomena that is called four-wave mixing. So in this experiment, so you have a silicon, the nonlinear material, a silicon waveguide. We have two photons, two pump photons that to annihilate in the silicon waveguide by generated spontaneously two other photons that are typically called the signal and the idler photons. And in the generation process, what you have to do is that you have to conserve the energy so that the sum of the energy of the two pump photons is equal to the sum of the energy of the signal as well as of the idler photon. And indeed, if you measure the generation spectrum, so the spectrum of light coming out your waveguide, so this is what you measure. So you see the very strong pump photon that is not spontaneously turned into the two signal and idler photon, as well as on the side, on the longer wavelength side, you see the peak due to the signal, as well as on the small wavelength side, you see the peak due to the idler. And if you sum up the idler and the signal, so you end up with 2 times the energy of the pump photons. And this assures you that you have conserved the energy. But as in any scattering mechanism in physics, you have also to conserve the momentum. And so you need to have that the momentum of the two pump photons should equal the momentum of the two idler photons. And here in our experiment, so this is called the phase matching condition. And here in our experiment, what we are using is that we are using the modal dispersion in order to get the phase matching condition by using different modes, different waveguides modes. So we use 2 different waveguides mode for the pump photons, as well as 2 different waveguide mode for the signal and idler photons. And the reason why we want to use these we want to use these different optical modes is because in this way, so we can generate the signal and the idler very far away in energy. So let's look to the simulation. So here is the simulation of the efficiency of four-wave mixing, spontaneous four-wave mixing generation as a function of the wavelength for a pump photon that is at the typical telecom wavelength. So here we have the pump photon at 1.55 micron, and we look at the idler wavelength. And what you see is that in the case we use the very same mode for the pump and the signal, the phase matching condition impose that the energy difference between the pump and the idler should be extremely small, because otherwise you cannot phase match the different waves. And so the generation is very high near the pump wavelength and then decrease dramatically. So this is in dBs. So decrease dramatically in efficiency as far as we move far from the pump wavelength. On the other hand, if we use different modes, for example, this one is the first order mode, and this is the second order mode for the pump in the waveguide, as well as we use the second order mode and the first order mode for the idler, what you see is that you get a very high generation efficiency far away from the pump wavelength. And so by using this intermodal phase matching, so you can generate your signal and idler photons far from the pump wavelength. As well as you see another very important consequence, the fact that the generation bandwidth is extremely narrow. So you get a far detuning as well as a very discrete narrow generation bandwidth. This is going to be very important for the last application I'm willing to discuss. So let's now change the waveguide width. And by changing the waveguide width, so we can get the generation of the signal photon in the mid-infrared as well as the generation of the signal photon in the near-infrared. So here is a typical example. So 2 micron wide waveguide. So we pump at 50-50, and then we generated 2 micron and at 1.3 micron. But now the issue is, how can we integrate everything, so this concept, into a single chip? And so this is the solution. So here is our waveguide, the structure of our waveguide that we are using. So this is an integrated chip where we are exploiting intermodal four-wave mixing between the fundamental TE mode and the second TE mode. And so the idea is the following. So we enter with the pump photon, then we have a 3 dB coupler, meaning that we have the pump photon and then we split the pump signal in 2 halves. So 50% here, 50% there. So we have 50% of the pump here and 50% of the pump there. Then we use an asymmetric mod coupler, which is the key device for intermodal four-way mixer on the chip. And in this asymmetric wave coupler, so we couple the first order mode of this waveguide with the second order mode of this other waveguide. So in this way, so we get the conversion from the first order mode to the second order mode here. And so that means that we can get inside the waveguide in this point 50% of the input power on the first order mode, and then by using this asymmetric coupler, so we get 50% of the pump power on the second order mode. And so now here we can get the proper pumping condition. Then we get the wide multimodal waveguide where the intermodal four-way mixing is happening. And so we do generate here the idler as well as the signal photon. And then in the output, so we use the same approach in order to extract from the waveguide one of the 2 modes. And so we use an asymmetric coupler to extract from the waveguide the second order modes. And in this way, so what we get at the output, so we get the signal, here the signal at 2 micron. There we get the idler photons, and here the residual of the pump line. So this is the design. So here is the actual chip that has been realized, and here are these results. So by measuring the output of the chip, so what we see is that we actually generated 2 micron, as well as we are able to generate 1.2. So we are able to demonstrate that we are generated the signal as well as the idler. And the pair generation efficiency, remember, so the 2 photons are time correlated. So the pair generation efficiency in our experiment with the weak milliwatt pumping power is in the order of a few millihertz. So you get a few millions of pair photon generated per second. And then we have to demonstrate that indeed we have a single photon, an heralded single photon source. And in order to do that, so what you have to do is that heralded two-particle coincidence measurements. So the idea is very simple. So you measure the idler photon, so you measure the heralder photon, which heralds the presence of the other photon. And then you use a beam splitter. And you will never have that the two detector clicks at the same time. Because if you have here a photon, a single photon, so either this detector is clicking or this detector is clicking. And so if you measure the trigger coincidence, so the heralded coincidence between between these two detectors, what you expect to measure is 0. And this is the outcome of the measurements. And so what you see here is that when we do herald our photon for a very low pump power, so that we are in a regime where multi-photon emission is prohibited, so then you measure a second order heralded coincidence that is lower than 0.5, that is the limit for claiming a single photon sources. And so indeed, so here we are able to demonstrate a single photon source by using our photonic chip. And actually the results that we are demonstrated are quite superior with respect to other results published in the literature. So now, so we have mid-infrared single photons, we have heralding with high generation efficiency, and we can use these for a quantum gas sensing. And here we have two concepts that we can use. So the first concept is spectroscopy. So you change the pump wavelength, so the pump photon wavelength, so that you can change the signal photon wavelength, and so you can make the spectroscopy on the absorption line of a single molecule. Here is an example of the carbon dioxide. Or on the other hand, what we are trying to do is imaging with undetected photon. So this is a concept that was proposed by Zellinger a few years, by the Zellinger group a few years ago, and which is based on doing imaging by looking at photons that do not interact with the object that you are looking at. And so the idea is to perform a quantum interference between two different nonlinear entangled photon sources. And in this experiment, you have that the photon that interact with the object is not actually the one that is used to perform the quantum interference. And so that due to the entanglement, so you are looking at your object by not using the photons that has interacted with your object. And so we are trying to perform this experiment on the chip, and I think this is very fascinating experiment. So last example, if I still have a few minutes, so the last example is to try to use this concept of intermodal four-way mixing in order to generate an ideal or near ideal photon source for quantum computation. So here the point is that when we want to have, or when we have a single photon, so this is a photon that is completely independent, has no correlation with other photons. On the other hand, in entangled photons, so you have very strong quantum correlation between the two photons in the pair. And so if you look at the properties of your single photon, you want to have an anti-Banchi statistics. That means that you have a true single photons. So anti-Banchi means that if you perform two second order coincidence experiment for a zero delay, you want to have that this second order coherence coherence function should be equal to 0. Then you want to have a pure state, so no correlation with other photons, and the ideal source of single photon should be deterministics and should be indistinguishable with respect to other equivalent sources. And the indistinguishability you measure by doing quantum interference experiment. So here the idea is that to start from entangled states and then break the entanglement. So you can end up with a factorizable state, and then you measure one of the two photons in the pair by using the heraldic concept, and you end up with a second photon that is in a pure state. And so by going more in detail, so essentially what we want to do is that we want to generate a photon pair that are characterized by joint spectral intensity that is like a pure spot. So let us have a look to this joint spectral intensity. Here is the intensity of the hydrogen wave function multiplied by the intensity of the signal wave function. And so typically in this example, so you see the joint density spectral, joint spectral intensity shape that show correlation, meaning that if you change the wavelength of the signal, you see that at the same time also the wavelength of the hydrogen change. And so you move from a very correlated pair where, as I was saying, so if I'm changing the wavelength of the signal, so also the wavelength of the hydrogen is strongly changing. So those are extremely correlated. To a situation where the pair is completely uncorrelated, so we change the wavelength of the signal without getting any change in the wavelength of the hydrogen. And so in this way, the two wave functions associated to the hydrogen and the signal are factorizable, while in this case, the two wavelengths are strongly entangled. And the way to measure the degree of correlation between the two photon states is to measure the purity of the state. So what you aim at is getting a purity equal to 1 or as large as possible or as similar as possible to 1. And if you have a strong correlation, you have a purity that's equal to 0. So the way to do that in four-way mixing is simple. So we start from a correlated case, and then we filter. And so by using a filter, so we select only those photons that are in this small spot here. So we filter the signal, we filter the idler photon, and so we end up with a joint spectral intensity that has the classical shape of uncorrelated pair. However, in this case, what we get a large purity at the expenses of the efficiency. And so the idea we have is that to use intermodal spontaneous four-way mixing. And the reason is because the discrete band of generation of the signal and idler photons allow us to get uncorrelated photon pair. And those are naturally filtered, so we do not need any further filtering, meaning that we get high purity as well as high heralding efficiency. However, here we have a problem. And the problem is the fact that we are in a situation where the two photons travel on different optical modes. Different optical modes means that they have different group velocities. And so while they are traveling inside the waveguide, so they get a temporal displacement. And so in order to account for those different group velocity, so we have produced a chip where we introduce arbitrarily a delay between the two pump photons, so that we get a strong overlap in time of the two photons in the region where we have the four-wave mixing generation. And in this way, so we can get very high purity. So this is the concept. Here is the experiment. So you have the pump photons, then you have the directional coupler. So 50% is going here, and then 50% is going there, where you see a serpentine that is used in order to delay the two photons, the two pump photons, in such a way that when they travel on the multimodal waveguides, where they produce the four-way mixing photons, so you get a very high overlap between the two pump photons. And so by using this delay and by using the intermodal four-way mixing, then we were able to demonstrate that indeed, so we are generated photon pairs with a very high heralding efficiency, very high purity, and very high indistinguishability. So the indistinguishability was demonstrated by integrating on the same chip two different sources and then performing a quantum interference experiment between the single photons generated by each one of those two sources. So here are the joint spectral intensity for the photon of one source and the photon generated by the other source. So you see a very high purity as before, and then this is the quantum interference experiment. And so we get a number of indistinguishability that is in the order of 90%, which is a very large number. So it's the first time that this very large number has been demonstrated. And so this source is an ideal single photon source with numbers both for very good numbers both for the anti-bunching statistics, the purity, the indistinguishability, and everything needed for really producing a near ideal single photon source on a chip. And why those are important? And those single photons are important for quantum computation. And quantum computation is actually a huge opportunity for silicon photonics, for quantum silicon photonics. And indeed here, you see that the company, which is Psi-Quantum in the US, is actually trying to building a quantum computer by using silicon photonics. And indeed, so this company has raised an extremely large amount of venture capitalist funds in order to be able to get to produce a quantum computer. Okay, by saying this, so I'm finishing my talk. So I want to briefly give you a few last remarks. So I hope to have shown you that silicon photonics is a mature platform to implement novel kind of devices. I hope to have shown you that integrated quantum silicon photonics is now on the market, so you can buy a mobile phone with a quantum random number generator based on silicon photonics. So there are a significant attempt to demonstrate a quantum silicon photonics-based computer in the next few years. And the reason is because quantum technologies can really take profit. I hope to have shown you a few examples of the dense integration, scalability, robustness, and low losses of silicon photonics circuit. And finally, I think that a lot of new physics and devices are still there to be discovered by using quantum silicon photonics. So I would like to acknowledge the people in my group because they have done most of the work. And actually, so we are looking for 2 postdocs in the neuromorphic photonics activity we have. So if you are interested, please send me an email. And specifically, I would like those who are participating in the quantum photonics effort that we have at our in my laboratory in Trento. I would like to thank also Professor Samit Roy for the kind invitation here. And finally, I like to thank the sponsoring, the project that sponsor our research activity, and specifically the India Trento project for advanced research. And thank you for your attention. Okay.
So thank you.